Okay, fluid structure interaction. You tell me first. I want to get your feel before I really start. I mentioned a few times here. What does it mean, fluid structure interactions? Other professors also are teaching the fluid structure interaction. And I bet you heard about the fluid structure interaction, or shock structure interaction, or acoustic structure interactions, vice versa. So, tell me in just a few words. Maybe start from Hassan.
I think fluid structure interaction means that the behavior fluid might be very adjacent to the solid structure. That means the behavior fluid.
Mm-hmm. So in a rat, simply speaking, as the word mentioned there, is interactions, right, between the fluid and the structure, simply speaking. So in underwater explosion, excitation is caused by the shock in water. So due to such excitation, then interact between the fluid and structure. That's right. But there are all different kinds of field. They use fluid structure interactions to use. This is kind of a very important. This is the beginning. And I mentioned to you already, this is really the beginning of a fluid structure interaction. And as I did in chapter 2, I use hydrodynamics relations, which is very easy to really see the implication. And I really explained all the physics base. Everything starts the physics base. But this, after this 10.3, I'm going to go into the chapter 5. Then I am going to really reveal a little bit different way, mathematical way, to really explain the wave equation. We draw the wave equation from the physics-based approach. Then I'm going to introduce this week is velocity potential. You heard? I read already from the fluid mechanics of fluid dynamics. And you already heard about the velocity potential. So I'm going to introduce, I assume you know nothing about the velocity potential, which is just mathematical approach to get to the destinations. Whether it's a physics-based, whether it is a mathematical-based, destination is the same. But between the procedure is slightly different. Okay, so that's what I'm going to do. So fluid structure interaction part. What I'm going to do is fluid structure interaction, usually called FSI. I'm going to do this week. Today is I'm going to introduce Taylor plate theory. This is a very simple, very nice theory to explain how the structure will interact, how the fluid, how the structure and the shock wave interact. And then I'm going to introduce the velocity potential. I'm going to give you a little bit the roadmap before I really start driving out velocity potential. Then I'm going to using the velocity potential, I'm going to express the wave equations. I'm going to not introduce wave, express wave equations using the velocity potential. Now you dive in the field of mathematics, then you can really express everything in velocity potential rather than hydrodynamics relations. Then express the wave equation as the velocity potential. Why we do that? We could ask that question. I was asked it before for kind of the very logical way of doing it. Physics-based approach, sometimes sign plus or minus sign kind of confusing. Should I put plus or should I put minus? But if you practice, of course, you can do comfortably eventually. But for mathematical approach or velocity potential approach, you don't have to worry about the sign. It automatically comes out as a result, for example. So there are a lot of benefits. But sometimes it's annoying, but this velocity potential approach uses quite a bit in all different fields. Then after this, I'm going to get into the extended field plate theory to explain, to show you the additional FSI. Tailor plate means flat, very thin flat plate, as I will explain. Then no curvature in it. So next I'm going to introduce spherical shell. Here. Using the spherical shell, I'm going to show you how fluid the spherical shell interacts. So then lastly, I'm going to just introduce so-called DAA approach, doubly asymptotic approximation approach, which was originally developed by Professor Tom Gears in early 1970, and it was a very powerful tool. Those years, computer capacity was pretty low. In other words, nowadays, right, you're using the PC, which is right in your the desk. I couldn't imagine how lucky you are. And I first worked in the industry. I worked at Naval Corporation in San Francisco. They built the nuclear power plant. In the 70s, worldwide, we started to build a nuclear power plant. So I worked in San Francisco as a first job after I got my doctorate degree. Then computer capabilities really not that great, but that era we thought, wow, this is really fantastic. Then in 60s, late 60s, we use electric car. And you have nowadays, you never saw a computer car. Have you seen a computer car? It has a souvenir. Never saw a computer car. Computer car is something like this. One statement, coding, coder, goes into one computer car. So in mid-60s, I carried tray of computer car to load into the system, and there is a card reader, so I put that in there, then push the button, then the second read pretty bad. And usually card jam. Then you have to stop, you have to retype, then put that in, try again, vice versa. Then in the 70s, the paper tape, and you punch to a paper tape, and you just read the paper, so to see. But still, 70s, it wasn't that good for computing power is concerned. Then there are a lot of mathematical approximation came in. Nowadays, we try to minimize approximation, use the approximation approach. Sometimes you do, but in my position, computing capability that you have right on your desktop so powerful. In the 80s, the stuff you have in your PC took about it could take about 2 rooms, at least of this classroom, to fill up all different equipment, peripherals, all the CPUs and all that. And now it's right in the desk. So I try to use or minimize the approximation approach, but rather using the more mathematical, more exact approach to get a solution. That's the way you should do, and even a better approach in the future. DAA is doubly the asymptotic approximation. In high frequency, it approaches to the correct solution, and the low frequency, again, it approaches to the correct solution. Okay? So it's a doubly, kind of makes sense approach. The middle, nobody knows what's happening. Middle frequency has no definite fields on the solution. So that doubly asymptotic approach to the right solution, exact solution, but in the middle. That approach is what we had quite a bit in the 80s, since it was developed in the early 70s. Russians, I have heard, after these solutions, at the beginning it was developed by the Navy research lab, then eventually published in the Navy. Then it used quite a bit until I used even until recently I used this method to get the solution shock problem, but I no longer use this because we have much better, more exact solution. But it's nice to know. So I'm going to introduce a little bit about the DAA, what it does, because when you hear in some place, then you know what the DAA means. Doubly acid solutions. And this is what I want to cover this week, or you could spill to early next week. Okay? So at least you know what I'm heading for. So today I'm going to introduce the Taylor plate theory. Taylor plate is a 10.3. We have a nose. And roughly, what's going on is the first is a physics-based approach. So, Taylor plate theory. This is developed by Professor G.I. Taylor. I believe he's a professor in the UK, United Kingdom. Physics-based theory, because that's the way I always start. And Taylor plate, when you hear the Taylor plate, I want you to think about very thin plate. It's an ideal plate, very thin plate. Doesn't wiggle, does not wiggle. It's really acted together. It acted together. It's the ideal plate. So it's a plate. One side is air. The other side is water. This is the problem that Professor Taylor, I'm not sure whether he's still alive or not. And of course, this vibrate, I'm going to say the U is the velocity of the plate. Act all together, that's the usual. Ideal. Okay? Then this is air, this is water. It's a shock wave is coming right into it. This is a plane wave. If we think about the spherical wave has additional time, a little bit more complex than you can handle. It's a very nice, simple theory. You can really see the inside by the physics. So I'm going to call this shock wave. I'm going to call this the incident shock wave. I is incident shock wave. Okay? So if this is a hit here, I use this over here as a PI. So I'm going to use the same thing here. I use P1. Sometimes I use a PI. It shouldn't bother you, right? Then shock wave, flat shock wave, plane wave, hit the Taylor plate, which is a thin, infinite plate, act as a one. Then if you hit it here, as I show over there, it's going to generate what wave? It's generating reflection wave. It's the same, very straight. Okay? It reflects, right? Good, right? Smart. Good. Then what do you apply? Newton's second law, right? But this is infinite, So I have to deal with the plate. The mass of the plate. What would be the mass of the plate? Infinite weight, right? Infinite mass. We can't handle. So we're going to deal with mass as mass per unit area. Make sense? So we're going to deal with mass per unit area. So I'm going to say mass per unit area is temperature. Newton's the second law. Mass times what? Acceleration. U dot. U, I said, is what? U is plate velocity, right? Plate velocity is not the fluid particle velocity. So here is U, or in the vibration, people uses U like a W dot. Some people uses X dot. Depends on whatever the location you use. In vibration course, X dot. X usually used as a displacement, dot velocity, double dot acceleration. So U dot is equivalent to what? X double dot, or W double dot. No problem. So inertial force is equal to what? Summation of all the external forces. External forces is P1 plus P2 on free. Some of you might say, what about sine? What about sine? P1 is to the left, P2 is to the right. It should be 1. The P2 may be minus. You might get that feeling. So that's one of the little drawback for physics-based kind of derivation. But we can look into this way. This P1 will hit, give a pressure to the plate, positive. P2 is kicking the plate and out, right? To kick the plate, pressing positive. Not the tensile, that's not giving a tensile pressure, it kicks. That's the way the reflection wave could come out in this is P2. You can think of that. It's wonderful to do it. So all you have to do is solve this problem. Solve this problem with something like interface conditions are there. This U and the P1 and corresponding fluid particle velocity behind the incident shock wave is let's call U1. Fluid particle velocity, and for P2 let's call U2. So this guy, as you can see right here, we are dealing right at the interface here. P is a scalar quantity, U is a vector quantity. So plate move in that direction, not the vertical direction. U1 is in horizontal, U2 is also horizontal direction, vector quantity. Then that's a very clear interface condition is U is U1 minus U2. I'm going to have to put the arrow because direction is concerned is in horizontal direction. Another relationship you know is P1 is rho C U1. Rho C is what? Rho C is called impedance, or some people call it characteristic impedance. So can you compute the value? Yes. You know the C. What's the C? It's the velocity in the water, and rho is mass density of the water. We know that. And another P2 is equal to rho C. This is all you need. This is all you have. And so this is the first order differential equation. So here I'm going to say U1 from here is U1 is equal to rho C P1. U2 is equal to rho C P2. Then plug into expression for U. So U is equal to P1 rho C minus P2 rho C, which is telling you that rho C P1 minus P2. P1 you know that. P1 you know. This is a P, not rho. This one is incident shock wave pressure. Incident shock wave P1 is a function of time T is P max times D to the minus P over theta. You know that. So here the reference T equal to 0 is the time it hit the target, right? T equal to, start from T equal to 0, right? That's what you have. Because here is not T minus T1. Directly T, look at this equation here. So this T is greater or equal to 0. That means reference time T0 start counting when the shock wave hit the target as T is equal to 0. So from this, you can now from here, P1 minus P2 is equal to rho C U. So from here you can find the unknown P2 is equal to P1 minus rho C U there. P2, we express the P2 reflection wave pressure as P1 non-pressure, U is unknown pressure, unknown the velocity, U is velocity of the plate. So if you plug this guy right into here, this is equal to P1 plus P1 minus rho CU. Then if you look at this 2 here, which is 2P1, it rings the bell to you, isn't it? And here is minus rho CU. Or can miss, right? So you can think of what was the 2P1? Where did you see 2P1? Really? That's for the rigid boundary case. The pressure experienced by the rigid boundary is twice of incident shock pressure. Then due to the flexibility of the pillar plate, that much pressure has to be relieved, right? So whenever you're dealing with a flexible structure, think this way: it absorbs some pressure on itself. How much? Rho C U. That much pressure is relieved. Instead of experiencing 2P1, then rho Cu amount of the pressure is taken by the structure itself. So already, by looking at that, you can tell from here. So what you have here is mu dot. This is all the main variable is equal to 2P1 minus rho Cu. I'm going to move this guy to the left hand side, mu dot plus rho Cu. I don't have to use that guy. Rho Cu is equal to 2P1. Okay. So in the vibration equation, something like you have this is C damper, this is K M X, and 2P. What's the equation of this is? What the equation of motion? Anybody can tell? Anybody can tell? It's a vibration. Which is n x double dot plus cx dot plus kx is equal to n. This is. Compare this and compare this. I'm going to write here as mu dot plus rho C U is equal to. In this case, in our case, we don't have any spring. I'm going to put in the spring later. So if you compare this, this is like this. So by looking at that, as I said, x dot is like a velocity. X is deformation. So much. So rho C over here, C is acoustic velocity, right? And over here, C is damper. So this is like acting as a damper. This is acting as a damper. Cushion. Act as a cushion. So this case here is air. This is water. Okay. Then onto it. the water is acting as a damper. It absorbs. What about the water is now in both sides? Then it has double damper. Just without deriving anything. Oh wow. So water one side is rosy, water the other side, both sides, then it acts as a double damper structure. Makes sense? Without, we'll do more thinking, but without thinking longer, oh, one side water, rosy, damper, another side is water. It's all called the flooded area in the ship and submarine. Water both sides. You have ship or submerged vehicle, then you have some area which is covered, sensor to the stick amount here. There's water here, but it can sense what's in the water. Temperatures all different time. As you look at this guy, like both sides is damper. So it has a less severe effect. So water, in that situation, this equation can damper twice as well. So you can put over here 2. Because this is a physics-based tasting already the effect. It's nice. So then you have equation you have a very, very nice equation, and u dot plus rho C u is equal to 2P1. P1 is P max theta minus T over theta over here. T has to be greater or equal to 0. That's the first order differential equation, homework number 1 today. So, first order ordinary differential equation should take less than 15 minutes. And homework. So then I want you to, this is all on what I explained over here. Over here. You can solve it. I don't know to practice at home. And submit next Monday. So the solution is like this. This is exponential exponent. This is e to the 1 minus beta e plus beta minus exponential minus e. And the beta here is rho C theta over the rest. If beta is large, what does it mean? If beta is large, then m gonna be infinitely small. What does it mean, infinitely small? Very light. Very light. It's a thin plate, even thin, it's very thinner. Think of this, if the local habitation occurs when? Oh, I said the house habitation, I said. Local habitation occurs. Local habitation. I mentioned briefly to you already. This is sometimes called the house habitation. Of course, we study the bulk pretty funny, right? We have done the local habitation. When the habitation occurs, if you try to cool the water, then habitation occurs. It's a thin plate. If beta is large, that means M is very small. M is very small means plate thickness is very small. And when the shock wave hit, then what happens? The plate will take off. So yes, if the tailor plate is very thick, when the shock wave hit it, it's not quickly, fastly take off. So when beta is very large, M is very small, very thin plate, then when the shock wave hit it, it takes off. In other words, initially everything is all intact between the water and the plate. So when the plate takes off suddenly, that means the plate tries to pull the water. And if you pull the water, cavitation occurs, which is called the local cavitation. Or hull cavitation, the reason for the hull is really like a ship, is almost flat. Not really infinitely flat, no. But it's so flat, zones are there. So they named this hull cavitation. When the hull cavitation occurs, shock wave cannot penetrate in the local cavitation zone. Some will cavitate because it's not like the air, trapped air between the hull and the water. You see the implications. So then P2, you can compute that. P2 is equal to P1 minus rho C2. Rho is here, you can express it. And now you can add P1 plus P2. That's the total pressure right on the hull, right on the tailor plate. And when the cavitation occurs, what happens? Total pressure cuts off. So P1, P2 is 0 when cavitation occurs. P1, P2 is the maximum pressure the tailor plate can experience, then equal to 0. Then at that time, the plate has the maximum velocity. Because P1 and P2 is a max at the time of cutoff. Okay? You can use this all the equation if you sit down. I'll give you all the kind of example problem. Then I assign you in practice as a very good, quick, and simple application. It's pretty good. You know, the approach. Exercise problem, I said the homework. I already assigned the homework. But also verify the solutions that 10.9 through 10.11, which is the I listed solution I want you to conform by solving the first order ordinary differential equation. I want you to conform the U, conform P2, conform P1 plus P2. Okay? It's really easy. That's all homework. That's what I said. Then I discuss about the beta. When beta becomes large, then what happens? P1 plus P2 becomes negative at very early time. I assigned another problem page to get you the experience yourself. When P1, P2 becomes, when beta is very large, then pressure P1, P2 become negative, which means cavitation occurs in it's called the cavitation. And pressure in front of the plate is cut up when P1, P2 is max because cavitation occurs right out there. If you said this is a P1 plus P2, if you said this set equal to 0 is right at the cutoff, then we can find the express using this equation. You can express the t value, okay? The t value, which has a maximum. Velocity at the time t. So here I said this is equal to 0, means P1 plus P2 is equal to 0. Then we do the T naught. Okay, replace T as a T naught. Then that's the time that maximum plate velocity occurs. Then after you got the T naught, then put back the value of the T naught into the expression for the U, right? For the U. Then that U is maximum the velocity, that's what it shows here. And so as you solve a first order differential equation, then you got the solution U, right? Then you got P1, P2, then you compute that, then set equal to 0, then you can get the time T naught, where the maximum velocity occurs, when you got that. And after that, you plug in the T naught value into the U, then that's the maximum velocity right here. I want you to go through all that and then I don't want to just sit back and watch. When you close your eyes, everything about it is bad. So should do it yourself. And as Louis asked for help before, if you need any help on devices, printing whatsoever, don't suffer yourself. Talk to TQU or talk to me direct and get the answer on time. Okay. Sooner if you have any help, assistance, don't hesitate. Any questions? I talk a little slow because it's beginning of exercise and beginning of beautiful phenomena. Flexibility reduced, but pressure reduced. Okay, next is I'm going to stop right here.